Hi everyone. So welcome to this IJCAI 2020 tutorial. This is the first part of the tutorial, and the topic of the tutorial is submodular optimization approaches towards state data and feature subset selection. Okay. So the first part of the tutorial will be presented by me. My name is Rishabh Iyer. I'm an assistant professor at University of Texas at Dallas, and I kind of mostly work on the areas around submodel optimization and data subset selection and feature selection kind of problems. The second part of this talk will be presented by Ganesh Ramakrishnan, who is a professor at IIT Bombay. Okay, awesome. So we'll get right to it. So I'll start by kind of giving a motivation of subset selection problems in machine learning, and then I'll actually talk about the. So the first part will actually focus on more of the theoretical and algorithmic aspects. So in this first part, we'll actually talk about combinatorial models for summarization. So this will include things like understanding the role of submodular functions, the modeling power of submodular functions, examples of kind of submodular functions, and so on and so forth. The second part of this talk, the second part of the first part of the tutorial will focus on optimization algorithms. So in particular, we'll study submodel optimization algorithms for different function classes and different constraints. We'll then look at optimization algorithms for different kind of real world scenarios. So things like streaming scenarios, distributed scenarios, and so on and so forth. Then we'll actually talk about some extensions to approximate submodularity and how a number of functions are not really submodular but approximate submodular, and what can be shown theoretically for such problems. And finally, we'll actually go over some practical implementation tricks, right? Um, and the second part will be covered by Ganesh. So Ganesh will actually focus on three specific applications. The first is data subset selection. Essentially, how do you select subsets of data, right? Well, why do you want to select subsets of data? You want to select subsets of data maybe to train efficiently, right? So you can reduce the training cost and the training time by say factor of 10 if you select a 10% subset. You might want to select a subset of data to actually label, right? So that means you have a lot of unlabeled data and you select only a subset to label. Therefore, you can reduce the labeling cost and so on and so forth, right? The second part will focus on feature selection, right? And in some sense, we'll also talk about rule selection over here. So why is this important? Well, you have kind of features today, and the features are growing, right? Particularly with deep neural networks, you have a growing number of features. So how can you select subsets of features so that you can actually compress machine learning models? The third part will focus on data summarization. So here we will actually address, so here we will talk about things like video summarization, image collection summarization, and text summarization. So you have massive amounts of data. How do you summarize this for human consumption? Okay, so we'll start with a kind of brief motivation, right? So there's a growing impact of deep learning and machine learning. This holds for a number of areas today, like personalization, robotics, logistics, autonomous vehicles, just to name a few, right? A lot of internet companies kind of lie over here. Search engines like Google, Bing, recommendation systems like Amazon, you name it, right? So you have large number of companies whether serving ads, whether serving, kind of recommending items to users or kind of product search pages, or whether it's just kind of giving kind of social media companies like Facebook, etc. Right? So all of these kind of involve personalization, and the second part is things like logistics and robotics. And again, this is actually a kind of growing area where more and more deep learning and machine learning is being used. And finally, there's autonomous vehicles and kind of related industries, right? So you have kind of areas like kind of standard machine learning, computer vision, natural language processing, speech recognition. All of these are kind of relevant to this, as well as numerous other industries. Well, so with deep learning, there is the associated. So essentially, deep learning can be thought of. So I'll just add a quick slide over here. So essentially, deep learning. Sorry. can be thought of having two aspects, right? The first is growing size of models. So deep models, typically you require extremely complicated scale of models to deploy and to use. And with the growing complexity of models, you have the growth in accuracy, right? So growing model complexity implies growing accuracy. But the second aspect is also growing data sets, right? And each of these in turn also produce side effects. So side effects include growing amount of cost in both deployment and training, growth in the cost of labeling, right? Kind of getting these large supervised data sets, there's a cost of labeling, and so on and so forth, right? So there is naturally this data explosion, right, which is associated with this growing data sets, and kind of large amounts of human and machine generated data is created by the minute, right? So how do you essentially find events of interest for humans to consume? And secondly, since deep learning models require massive amounts of data and they're extremely compute intensive, how do we essentially make deep learning more efficient? Okay. So deep learning is extremely data hungry, and this is clear as you can see over here. You have kind of growth in the amount of accuracy as the number of data points increase, right? So this is just one such example. The y-axis here is the mean average precision. The x-axis is the number of examples in millions, right? And this is the performance of object detection. So one of the side effects of growing amount of data required for deep learning is the staggering training cost of deep learning, right? So training a BERT model, for example, would cost somewhere between $10,000 to $200,000, depending on the data set and depending on the configuration and so on and so forth, right? Similarly, training a single deep model for NLP with network architecture search, this is again with this particular paper, the back of the envelope calculation is that it would cost around $1 million to train such a model, right? Training a Elmo model, again, would take 14 days, and training a YOLO V5X model on a V100 GPU would take around 8 days, right? So that means that there is a large amount of cost involved in training such models. There is a lot of time involved as well. The second problem is that labeling large data sets is very expensive, right? So each of these cases, whether it's classification, object detection, 3D point clouds, or text classification, the cost is somewhere between $50,000 to $150,000 to $200,000, right? So that's approximately the range of labeling just 50,000 examples. But many of these problems actually require much more amount of data, right? So a critical need today is to be able to do machine learning in a data efficient manner. The second aspect, or sorry, the third problem. So the first problem was the cost. The second problem was the first problem was the training cost and time. The second problem was a labeling cost. The third problem is again, this is very relevant for real world data, is the noise and imbalance in data, right? So you have an increasing occurrence of the long tail problem here on the left, where you have certain classes which are underrepresented. So there's a kind of large imbalance. And again, Ganesh will actually talk about this more. So I'll just skim through this very quickly. The second aspect is the noise, the label noise, right? So you have a lot of this data generated from the web, from web search, and web search oftentimes is noisy. So you have label noise. The fourth aspect, or the fourth problem, is the data overload for human consumption. So this is something we face all the time, right? I face this every day. I have so many pictures being taken, and I just fill hard disk after hard disk with these pictures. It will probably take me hours and hours to really go and kind of segregate these images, right? Is there a natural way or a kind of simple way automatically to be able to segregate the images and kind of provide me the right kind of images that I need, and probably delete the images that I don't need, right? So how do I summarize large amounts of data? And of course, you want to keep many factors in mind when you're doing summarization. You want to keep You want to keep kind of the personalization aspect, the user specific intent of summarization in mind. You want to keep maybe potentially certain queries that you really care about, certain privacy constraints, and so on and so forth, right? All right. So a kind of main focus of like the second part again of this tutorial would be the efficiency of machine learning, right? So and in some sense, while this is kind of growing, can see that most of the papers actually are kind of increasingly focusing on accuracy as opposed to efficiency, right? But there is still a growing trend where a few papers now are kind of studying efficiency as well. And I think this is really important, right? So there's this growing trend now in machine learning, particularly recently in the last 2 3 years, with obviously kind of fueled by the growing cost and the growing time consumption of training these deep neural networks. Except for a few large corporate companies, most companies really don't have the resources. Most academic labs don't have the resources to train such large scale machine learning models. The second goal, like as I was pointing out earlier, is how do you effectively consume this growing amount of data, right? So this tutorial would focus on this in some sense part one. So part one would focus on the algorithmic and the theoretical aspects of summarization, data summarization, and data subset selection. And part two would focus on efficient learning and efficient visualization, right? So this includes, we'll talk about data subset selection, feature selection, and summarization, right? And part one, we'll actually talk about modeling. We'll talk about submodular functions and the modeling aspects and the algorithmic aspects. Okay. All right, so I'd like to acknowledge a lot of my students and collaborators and friends that I've kind of worked on this topic in the last several years. So I'd like to acknowledge a lot of their collaborations in this, and also they themselves have published actually a number of papers in this area. So this is not just going to be my work, but also a number of other research labs that have been focusing on this particular topic. Also, like to acknowledge Jeff, Bill, Stephanie Egelka, Andrea Scroza, Kai Wei, Vishal Kaushal, Michael Gigley for some of the slides that I borrowed to make this tutorial. Okay, so we now come to this big data problem in machine learning, right? Inherently, there is, and kind of this is something that people have realized in the last 10 years or so, that there is really a need for big data in machine learning, right? So, for example, this is just one example that Hayes and Efrose in 2007 conducted some initial experiments for an image completion problem, and they saw that with 10,000 images, the results were very discouraging. But when they actually increased the image collection to 2 million, they immediately saw kind of a jump in the performance, right? This is natural, right? Because big data really has all the patterns that you want to learn, and this will really help in kind of training a machine learning model. The converse side of this is that big data is plagued with redundancy. And the big question, really, that kind of I'm really interested in is that how can statistical predictions and actions be made cost effective with the right small data, right? So we are not saying that we just use any arbitrary small data. That is not going to be useful, right? We want to be able to use the right small data, and the right small data hopefully would be more similar to the big data as compared to the kind of random small data, right? So I'll just kind of highlight this point. So so the goal of this in some sense, this entire tutorial and kind of my focus right now is to find the right small data, and hopefully this right small data would be comparable in performance to the big data, which is much better than a random small data. And again, I'm just providing some kind of a peek ahead over here, just so that you're kind of motivated from this tutorial. So we'll see, for example, in the second part provided by Ganesh, we will see that just as an example on CFAR 10, right? So we do data subset selection on CFAR 10, and we'll actually talk about an algorithmic technique that achieves this. With just 10% of the subset of CFAR 10, we are able to get a performance which is about 2 to 2.5% lesser than the full accuracy, right? So the full accuracy is around 94%, and we get around 92%. Um, with just 10% subset, right? And this is through a kind of efficient learning slash data subset selection scheme. It's of course an adaptive data subset selection. So the data subset changes every few epochs. So it's not training on a fixed subset. The subsets can slightly change as the learning progresses. But the algorithm at any given time is just focusing on a very small subset of data. And this very simple idea actually gives around 12% boost over a random subset. So if you were to just do this naively by taking a random subset, throwing out the rest, it would get around 80% accuracy, right? So we get 92%. So again, this is the kind of main summary, if you will, of this tutorial, that how do we find the right small data such that it is comparable to the big data and much better than the kind of random small data. Okay. So I'll just kind of illustrate this again, right? So in some sense, this is like, maybe this is like random small data, right? You have some idea of the patterns here, but it's not complete in any way or form, right? Okay, you get a little bit more data. Again, this data is somewhat random, maybe slightly biased, not completely random, though it's kind of slightly biased because just giving you part of the story, right? But it's a little bit more data again. Then you get more data, right? And then you kind of understand that there is some more information that my small data is missing. And finally, this is big data, right? So big data has a lot of patterns. Well, one, it kind of has information of what is the feature space that is being covered, right? So this is like x1, this is x2. This is just two-dimensional data. It kind of covers the regions of where the points hold. But not just that, it also has density information, right? So it has, for example, that okay, this particular piece is kind of highly dense and populated, and here there are many samples over here, right? Conversely, this piece is dense, and on the other hand, these pieces are slightly sparser, right? So data is mostly focused on the middle. So there's kind of information like this that is there. Secondly, we also potentially have class information, right? So there is maybe some decision boundary that supports that kind of that separates this class. Okay. So now, just as a thought experiment, that think of this like machine learning. I'm sure all of you have studied this in standard, support vector machines in kind of standard machine learning, right? If you were to if you were to train a decision boundary, right? So say a support vector machine, say this is just, sorry, I'll just make this a little bit more clear. So say this is a binary classification, right? So I have my positive examples here, I have my negative examples here, right? In theory, if I were to be able to train a model, I would be able to know that, all right, this region is comprises of my negatives. Maybe I just need to focus on this part of my model, right? And conversely, this is my positive, so I just need to focus on this. I can kind of completely ignore this area, right? Because it would not really matter as much. For example, my support vector, my kind of so in some sense, these are my support vectors, right? And the decision boundary really depends more upon these kind of the examples here as opposed to the examples far away, right? The second aspect is I also want diversity, right? So if I have if there is a lot of redundancy over here, then maybe the redundancy is not that great, and I can kind of eliminate the redundant examples and I can get diversity, right? So that's where I mean by the right small data. So this is one example of a core data or a summary, right? This core data is more from a representation perspective or a diversity perspective, right? But if you kind of additionally add that, this is being used, for example, for training a machine learning model, then you might kind of have this information as well, right? So you might want to get kind of more points that are close to the decision boundary for kind of support vectors. So things like this is what we will actually study in this particular tutorial. Okay, awesome. So I'll quickly point out that there are actually several flavors of similar tutorials that have been done. Those tutorials have been slightly more focused on the algorithmic and theoretical aspect of submodularity as opposed to directly up kind of the applications itself. So things like the ICML tutorial, maybe there was actually a workshop for several years at NURIP/NIPS. There have been some tutorials at ISIT, and a few different tutorials on data summarization at CVPR. Um, all right. So with this, we'll actually now talk about submodular functions. And actually, we'll first talk about basically the definition of submodularity, the modeling power of submodular functions, examples, and so on and so forth. Right. Second part of this, the of part one, would focus on optimization algorithms. Okay, so um, let's see. All right. So imagine, so basically, I kind of define some terminology right now, right? So we define V as essentially the ground set, right? So this is also called the ground set, right? Or it basically is the set of all possible data points in my universe, right? So I'm essentially talking about subset selection, right? So what what does it mean by subset selection? Well, you're selecting a subset of something, right? So that something is a ground set. So ground set is my entire set of data points. Could be my entire CFAR10, it could be my entire image net, right? And I want to select the right subset of this. So one way that subset selection problems are kind of modeled is that you define a valuation function f that applies to each subset, right? So I have my entire ground set over here, v, right? And I have my f, which goes from 2 raised to v to r. What does 2 raised to v mean? Is that it basically is a set function that applies to any particular subset. There are 2 raised to n number of subsets, so that's why there's the notation 2 raised to v, right? So this means that any subset A of V, you can apply this valuation function, right? So I take the subset A and there is a cost associated with this subset, right? So F measures this cost. All right. So as you can imagine, if there is no specific structure on F, then optimizing this is very hard, right? So in general, this would be NP hard. It would not just be NP hard, it would be even NP hard to approximate, right? So you cannot even get any approximation guarantees. So what if there is some special structure? And one such special structure is the property of submodularity, is what we would talk about in this tutorial. And we will actually then in part two connect how several of the data selection slash feature selection slash summarization techniques actually kind of rope in back to submodularity. Okay, so what is submodularity? So submodularity is actually a very, very intuitive diminishing returns criteria, right? What it basically says is that the as you go from a subset to a superset, so as the context of the set grows, the gain of adding element shrinks, right? So define here a particular subset here A, right? And I have a new item V, right? And this is a subset B, and I have a new item B, right? So f of A, define f of A as the number of distinct colors of the balls in the urn, right? So here there are two distinct colors, so this is 2, and f of A union V is equal to 3, right? Because there is a new blue color being added, so the number of distinct colors grows from 2 to 3. Similarly, f of b is equal to 3 already, and since blue color is already there, this is also 3. So the gain, which is f of v given a, right, in this example is actually 1, which is greater than the gain of adding v to b, which is 0. Right? So what submodularity says is that as I have more information, a new item adds lesser and lesser information. This is very, very, very intuitive, right? Any information function You have a set of items, you want to model the information content of the set of items. It would intuitively be submodel. The negative of a submodular function is supermodular, right? So what supermodular means is that as I add more items, in some sense there is a gain, right? So it goes, so basically the marginal value of adding item increases as the context of the set grows. So in some sense, the supermodular function is more akin like a convex function, right? So essentially a convex function is something like this, right? So as you increase in terms of the size, or as the context of the set grows, the gain increases, right? So the gain, for example, over here is only this much, but the same gain now is much larger, right? So as the function grows, so this is supermodular. Conversely, submodular function is a concave function, right? Because as you mm, so again, as the size grows, so well, this is a decreasing concave function, but you could also have an increasing concave function, right? So you could have a concave function which looks like this. So initially, the gain is large, right? Sorry, yeah. So basically, this is the gain initially, right? And then as the set grows, the gain shrinks. So the gain shrinks to something small. All right. So again, this is another way of kind of of thinking about submodularity, that you kind of from the perspective of cooperative cost of discounts, right? So the more items you buy, the more discount you would likely get. So imagine that you buy a hamburger and fries, you are more likely to be thrown in the Coke for free as opposed to when you just buy fries, right? So there's this discount that you get the more items you buy. There are actually two equivalent definitions of submodularity. The first is diminishing gains, which we saw. This is the diminishing gains definition, right? And the second definition is the union intersection, which says that f of a plus f of b is greater than equal to f of a union b plus f of a intersection, right? And the union intersection definition actually holds with equality. And similarly, this also holds with equality when the function is additive or modular, right? So we'll actually see this right now. Next, that a set function is modular if the gain of adding an element e to the set A is independent of the set A, right? It just depends on e. So it is we, or it is equal to f of e. Okay. All right. So we also say that a function is monotonic, or monotone submodular if, as the context of the set grows, so as you go from a subset to a superset, the information function also grows, right? So that means that um, when A is a subset of B, f of A is actually less than equal to f of B, right? So as you go to a larger set, it has more information. This is very intuitive, right? And number of submodular functions like influence functions, entropy functions, information gain, etc. They are all monotone submodular. Okay, so now we'll spend the next few minutes actually talking about the modeling power of submodular functions. So yeah, so essentially think of submodular functions from a perspective of summarization, right? So when you're summarizing a large data set, you want to model a function that can store the information content of a subset, right? So imagine now I have a subset A and I have a subset B, right? Think of the information as the number of distinct scenes that are there in the image, or the number of different people that are there in the image, or just the information that the image provides us, right? And somehow you want to kind of model this as an information function. So as you go, so you have, again, recall this is A and B, and now I'm adding this element V, right? As I go to a superset, it is more likely that there's going to be something. So again, this is V, right? That there will be something that is similar to this new item as opposed to the subset, right? So as you see over here, the gain of V given A is actually going to be greater than f of V given B, right? Hence, this is submodular. So again, this is just a proof by figure, but you would expect that a lot of summarization and data subset selection problems are submodel, right? So now we'll actually take a look at a few different examples. So we'll take a look at some representation functions. So we'll see, for example, facilitation and graph cut as examples of representation functions. You look at diversity functions. We take a look at coverage, importance, information, discounted costs, and complexity, right? So I think these are like different facets of submodularity that we'll see. So we'll start with information. We'll start with representation. So what does representation mean? Representation means that I have my data set and I want to find a subset that somehow represents this entire data set, right? What does it mean? It means that wherever I have clusters of points, I should have a kind of representation for my summary in those clusters. Essentially, what this means is that if there are some outliers, for example, here, right, my summary may not focus as much on the outliers. It will focus more on the kind of points that are more clustered or more representative. Right. So again, this is an example. I have these clusters, and as you see, the summary kind of picks points from each of these clusters, but it completely ignores the outlier point over here. Right. One example of a representation function is facilitation. Right. This objective, in fact, is actually very similar to um, is actually very similar to a k medioids objective, right, which is sum of I in v max k in x sik. And again, I'm not going to spend too much time right now, but you can kind of see the similarity, right? So k medioids actually operates on distances. So instead of a max, it's a min, and instead of maximizing the fetch location, you're minimizing the k medioids, right? But essentially, they are both connected by just a minus sign. So as we can expect, representation functions will pick centroids. So as I said, right, facilitation is very similar to k-medioids, and then there's this other problem called metric k-center, which is more of the robust version of this. This is not submodular, but is actually kind of related to submodularity, and it turns out that there is a similar greedy algorithm that applies. So of course, we'll take a look at these algorithms a little bit later. Okay, the second kind of functions is diversity functions. And diversity functions essentially mean that I don't really care about representation. I just want my points to be as far away as from each other as possible, right? So again, imagine that I have, even though I have these clusters, this time actually I took an outlier point in lieu of a kind of more central cluster, right? So even though there are three images over here, my diversity function does not care about the number of images. There could be 10 images here, but just because it's kind of similar in some sense to some of these other images, right? It doesn't think it's diverse enough, right? So what diversity focuses on is kind of getting points which are as far away and diverse as possible. So this is another dispersion function, which is minimum pairwise distance. This also turns out to be something similar to pick points as different as possible. Another kind of function is coverage functions, and coverage tries to select a subset so that it covers a set of concepts, right? So imagine I have a set of documents over here. So this is D1, this is D2, and so on and so forth, right? And each of my documents now cover certain concepts. This is an image example, right? So I have my image here, and this image covers a car, this image covers a car, this image covers greenery, it covers a male, and so on and so forth, right? So there are concepts covered here, and now I want to get a minimum subset of images. So I will get basically, for example, this image, this image, this image, and this image, right? And this subset already covers now all of my concepts, right? So in some sense, this is like similar to diversity and representation, right? But it's yet slightly different. Here you can arbitrarily define these concept spaces and define then coverage functions on these concept spaces. Another example is probabilistic, and the probabilistic set cover function does not necessarily force a particular does not kind of force a hard assignment, right? So you don't need that this image should only have a car. You can say that with a certain probability there's a car, with certain probability there's greenery, with certain probability there's a beach, and so on and so forth, right? So you have this probabilistic vector. So each image has this probabilistic vector Pij, and then you define this probabilistic set cover. So if my Pij's are binary, I get back my set cover function. So this is in some sense a generalization of my set cover. Another example is feature-based functions. Feature-based functions operate on features induced by models and try to model diversity across the features. Again, this is somewhat related to coverage because each of my features covers certain concept space, and I want to kind of get a coverage or a diversity across these feature spaces. So that's what is induced by feature-based functions. An extension of feature-based functions was recently studied called deep submodular functions. So deep submodular functions basically kind of do this hierarchically, and in some sense, you can kind of learn an end-to-end deep model which learns the features and also kind of is aligned with the submodular function, right? So this is kind of known as deep submodular functions. Finally, we look at information functions. And information functions are essentially functions that are defined on random variables. So in particular, you have a subset of random variables. You can define the entropy of a subset of random variables. And this entropy of a subset of random variables, you can kind of model the information content of this, and this is it itself turns out to be a submodular function, right? So if I model h of xs, where xs is the joint basically is the variables indexed by subset s, and h of xs is the joint entropy of all of these variables, this function turns out to be submodular. And actually the proof of this is remarkably simple. So the proof basically says that it kind of goes by the idea of information never hurts. So that means that you can basically define the gain of adding an element to a subset A, and if A is a subset of B, right, then you kind of have this diminishing returns by the information never hurts property, right? So discrete entropy is a submodular function. So motivated by the connections to entropy, we'll kind of take a slight detour and study what is known as submodular information measures, which was kind of recently studied and kind of connected with various applications of machine learning. So I'll go over this a little bit quickly, but I'll try to give the main idea of what's going on here. So again, recall that you can define the entropy of a subset of random variables. Given two subsets A and B, you can define the mutual information between XA and XB. And this is kind of the standard mutual information, the entropic mutual information. You can define the conditional entropy, which is H of XA given XB. And finally, you can define the conditional mutual information, which is the mutual information with XA, XB given XC. So it turns out that that kind of in the early days, Shannon, I think in his 1948 paper or maybe sometime later, actually kind of studied the concept of the inequalities captured by entropy, right? And he said that there are three fundamental properties of entropy. One is that it's actually normalized. So that means that the entropy of the empty set, or there's no random variables, it's zero. It's monotone. So that means that as you add more random variables, the entropy only increases. And third is what he called the two alternatives, is basically submodularity, which entropy satisfies, which is f of a plus f of b is greater than or equal to f of a union b plus f of a intersection b. So he said that these three properties are actually kind of characterize entropy, and you can get a lot of the inequalities from these. Right? So you can characterize entropy using this. Well, Shannon didn't know whether this class of functions is exactly entropy or not, and that is what we actually see. It turns out it's kind of the class of submodular functions or polymetroid functions. Since it's monotone, the class of monotone submodular functions or polymetroid functions is strictly more general compared to entropy, right? But essentially, from property 3, we actually get the non-negativity of mutual information and non-negativity of conditional mutual information. And properties 1 and 2 imply the non-negativity of entropy and conditional entropy, right? Exactly. So essentially, you can kind of generalize this to say that the function, any function f satisfying these three properties is exactly the class of what is known as polymatroid functions, right? So the question is that is polymatroid functions, or actually are polymatroid functions, sorry, equivalent to entropy or entropic functions, right? So it turns out that unfortunately no. Polymatroid functions are actually richer than entropy functions. Um, so I'll kind of quickly come to this and then I'll jump back, right? So this was shown in actually much later in 1997-98 by Zhang and Jung, where they showed that actually entropy also additionally satisfies certain inequality, um, which in general polymatroid functions may not satisfy, right? So there are examples of polymatroid functions which actually do not satisfy this inequality, but entropy actually satisfies this inequality. So what this means is that entropy is actually a kind of more restricted class of information functions compared to submodular information or polymatroid functions. So this now kind of motivated us as well as several others to actually study what do we exactly mean by submodular information functions, right? So you can define a standard information function or a submodular function basically as this function f of a, but now you can define submodular mutual information as the mutual information between two subsets a and b, right? As I f of a comma b as f of a plus f of b minus f of a union b. Then you can study the conditional gain, which is f of a given b as f of a union b minus f of b, and finally the conditional submodular mutual information, which is I f of a comma b given c, and this is f of a given c plus f of b given c minus f of a union b given c. So what is the intuition going on here, right? Well, submodular information is just the information of a subset A, so it's clear from the name. Submodular conditional gain is the gain in information of adding a set A to a set B. So this is essentially f of A given B, right? The mutual information is the joint information between A and B, but this joint information depends on the function f. And finally, we can also study the notion of independence as what are kind of which sets A and B are independent. What does it mean for A to be independent with respect to B in terms of this function f? Okay, so I'll quickly define again a generalization of this to K sets. So this is called multi-set submodular information. So you can define a total correlation, and also you can define actually the multi-set mutual information of this. I won't dwell unfortunately too much on this. If you want, you can take a look at our recent Alt 2021 paper where we actually introduce this. But actually I'll step back now and actually try to understand this using some examples. So let's take a look at weighted set cover, right? So you recall that you have a set of documents D1, D2, and each document covers certain set of concepts. And now you can define gamma A as my covered set of concepts, right? And f of gamma A is nothing but a weighted covered set, right? I kind of forgot to mention this, but when you're looking at set covered, you can also associate weights with my concept space. So imagine you're doing summarization and you have your words and you want to kind of find a summary that covers as many words as possible. Well, you can assign a weight to each word, and the weight can be essentially how unique the word is. For example, like something like TF-IDF, right? So imagine you have words like is, at, that. These words kind of appear very frequently. You don't want to really consider those as much in summarization, right? So you can assign these weights when you're doing summarization. Similarly, you can define f of a given b as w of gamma a minus gamma b. And again, this is very interesting, right? Because now the conditional information of f of a given b is actually the weighted sum of the concepts, the concept difference, right? So it's gamma a minus gamma b. So essentially, imagine that set A covers 5 concepts, and but set B, even though set B is much larger, it actually covers the same 5 concepts. the additional information is actually zero, right? Um, IF of A comma B, which is the mutual information, is the joint information between gamma A and gamma B, right? So it's W of gamma A intersection gamma B. And again, this is also intuitive, right? So I have, so instead of looking at how similar my sets are, it could be possible that A and B are completely disjoint sets. But if they cover the same set of items, that means that their mutual information is high. And similarly, we can actually define these extensions of um, multi-set mutual information and independence. Independence is very interesting. So independence means A and B are independent, not necessarily if they are disjoint. They could be disjoint, right? But they are independent if they cover completely different sets. So there is no intersection between their covered sets. Again, you can do facilitation. This is a standard facilitation. Kind of talk a little bit about the mutual information, right? So the mutual information here is you're taking a min between the amount of representation. So recall, facilitation is a sum over I in V. Kind of takes how well is my current point V represented by set A, right? Now what I'm doing is that I'm taking the minimum of the two representations, right? So the mutual information or joint information is what is the minimum amount of joint representation that each of my points have on the entire set, right? And I take a sum of this. So this I think very interesting and potentially very useful. I'll skip this. There's another function. Again, you can kind of define the IF. Okay, so actually I'll talk about this. So it turns out that with this particular function, you actually get exactly the graph cut function. So this is the sum of I in A, I in the sum of J in B, Sij, and you take the IF of A comma B minus A, right? This is exactly the graph cut. So graph cut itself is actually a submodular mutual information function. Similarly, you actually have a form for probabilistic coverage. All right, so like why submodular mutual informations are interesting, right? Well, they're interesting because you can actually kind of come up with some mathematical properties of this, but beyond the mathematical aspects and the kind of mathematical niceness of these functions, it turns out to also be relevant for many real world applications, in particular summarization, right? So thinking again of summarization, you can now, in addition to modeling aspects like diversity, coverage, representation, you can additionally also model aspects of query relevance. So imagine that you're taking the mutual information between A and a query set Q, right? I want to model in terms of F how much joint information is there between A and Q, right? So this is the submodular mutual information. Can also define the submodular conditional gain as F of A given P, right? And now this is that what is the additional information A has over and above P, right? So you can think of this from a perspective of irrelevance or privacy constraints, because in some sense what this will do is this to try to maximize f of a given p, it will try to get a set A which is as different from p as possible, right? So this equivalently can be thought of like minimizing the mutual information between A and P, right? Or trying to make it zero, for example, try to make it independent. So all right. So I think with this, we will almost kind of conclude this part of the motivations and the examples and the modeling capabilities of submodular functions. So I'll conclude this by just kind of giving the different classes of submodular functions. So as you can see, most submodular functions are actually monotone. So in some sense, they are kind of natural information functions. As you increase the context of the set, or sorry, as the context of the set grows, the information grows. But some functions are actually not monotone. An example of this is diversity, right? Diversity kind of models how far away or spread out the function is. And if I add new points, I could actually reduce diversity a little bit, right? Because imagine that you have 2 points, so you have 4 points that are very far away, right? And now you kind of add a new point over here in the middle, or maybe you add another point here, the diversity reduces. So think of like the minimum pairwise distance, right? The minimum pairwise distance actually now reduces because your point is now very kind of close by, right? So a lot of these functions are actually non-monotone, and there are a few functions which are even non-submodular or not submodular. And we will actually look at now classes of algorithms that handle each of these cases: monotone, non-monotone, and non-submodular. All right, so this is just a kind of a visualization. You have the supermodular functions, you have the submodular functions, you have the intersection over here, which is essentially the class of modular function, which is basically both a submodular and supermodular. Then you have the class of like monotone functions, right? And then you have the non-monotone functions, and finally dispersion function. The dispersion function are examples of non-submodular function, right? So the general class of set functions, and of course you have kind of weakly submodular, approximately submodular functions, and this is essentially where you can still give some theoretical guarantee. Okay, so now with this we'll study optimization. Okay, so we will kind of, so it will help us a little bit to think of this master optimization problem, and this master optimization problem which we'll focus on in this tutorial is submodular maximization, right? So since we are kind of thinking of submodular functions as information functions or diversity functions, right? You want to maximize the diversity, right? You want to maximize information. So for example, think of the application of data subset selection, right? You want to find a subset of data points which has as much information as possible. So given a budget constraint, for example, you want to find a subset of 10% which has as much information or has as much information as the full subset, right? So that you can find the right small data. So as a result, we will focus on submodular maximization. But having said that, it does make sense to study submodular minimization as well. But we won't actually focus it in this tutorial because it's not as relevant for kind of summarization, data selection kind of problems. Okay, so you have you have basically the master optimization problem, and you are maximizing here f of a, and typically there will be a constraint, right? So constraint could, for example, be a size constraint, that my size should be at most b, right? So say 10%. But I could also have a budget constraint where this is a knapsack, right? So we'll actually study why or where knapsack makes sense and what exactly is a knapsack constraint. F here could be monotone, non-monotone dispersion functions, non-submodular functions potentially, right? And typically we will think of this as F modeling, models aspects like diversity, representation, coverage, information, importance, so on and so forth. Okay, so now we'll talk about the first class of submodular optimization problems, and this is monotone submodular maximization, right? So this problem basically asks the following: that can I maximize, can I solve this optimization problem where I'm maximizing over s of f of s such that the size of s is less than or equal to k, right? So this is my constraint, and as I was saying, this is just a simple budget kind of a size constraint, right? And here C of S is equal to size of S, right? Um, the algorithm actually for this is very simple. It's what is known as a greedy algorithm. And the idea of the greedy algorithm is that I have my current subset S, right? So I have my current subset S, and amongst my rest of the item, which is V minus S, I'm trying to find the item E that has the largest gain. So I'm trying to maximize E in V minus S of F of S union E, right? Equivalently, you can also write this as F of E given S, right? Because this is F of S union E minus F of S. But when I'm searching over E, F of S is constant, right? So the same as maximizing F of S. So I basically take the argmax over here, right? This is exactly what this step is. And once I find my argmax, I just add it. Because the function is monotone, this quantity is guaranteed to be greater than or equal to 0, right? So what this means is that by adding this, I am guaranteed to not reduce my objective value. So without loss of generality, we can assume that my subset f of s, or sorry, that once I solve this, right, I get sk, the size of sk will be equal to k. I can assume this without loss of generality, right? That I basically continue this till I add k items. So the question is that how good is my subset SK, right? So this is measured in terms of approximation guarantee, and typically what we want to say here is that we want to say things like f of sk is greater than or equal to alpha f of s star, right? So alpha, which is less than 1, is my approximation guarantee because of the maximization problem, right? So my opt could be, for example, 100, right? And I can guarantee, my algorithm can guarantee theoretically, if say alpha is zero point 0.8, it can guarantee that I will get at least 80, right? This particular algorithm gets at least 80. In practice, though, right, it doesn't mean that in practice I will get 80. In practice, I would likely get 95 or 98, right? And that's what we see with greedy algorithms. So in practice, greedy algorithm gets an approximation guarantee of 0.98, right? For many problems. In practice, it works really, really well, right? And it's a very simple kind of myopic greedy algorithm, just looking at one step at a time and adding an element, right? So it's very simple, very easy to implement, very scalable, and hence very natural for subset selection problems, because as we will see actually later, it makes sense for subset selection itself to be extremely, extremely fast, right? So it should be lightning fast. And in some sense, the greedy algorithm and some of it is some of its variants, as we'll see later in this section, will provide us. All right. So how good is greedy in theory, right? So this was a very, very old result by Nemhauser et al. In 1978, where they actually showed that a greedy algorithm satisfies f of sk greater than or equal to 1 minus 1 over e of f of s star, right? And this is the optimal solution. Um, they also showed that no polytime algorithm can do better than this in worst case, right? So what this means is that in theory, this is the best we can achieve. This factor is roughly equal to 0.63 of the optimal, right? Um, and it turns out that the proof of this actually is relatively simple. I'll maybe spend a minute just going over the main idea of the proof, right? So define AI to be the chain of sets formed by the greedy algorithm. So recall that the greedy algorithm starts at the empty set. It keeps adding elements, right? One at a time. So at iteration I have the subset AI, and this has elements V1 to Vi. Denote A star to be the optimal solution in any arbitrary order, right? The order here does not matter. And F here is a monotone submodular function. We'll assume that um, f is greater than or equal to 0. So actually, by the way, this is taken from a blog over here. I'm kind of just kind of source, just acknowledging this blog, and then define OPT as f of a star, right? So what we will prove is that f of ak is greater than or equal to 1 minus 1 over e of OPT. So what's the proof? Well, so the main proof is actually just 5 or 6 lines, right? The rest of it is kind of just some manipulations on top of this. So the main proof follows as follows. We start with f of a star, and f of a star is less than or equal to f of a star union ai. This follows from monotonicity, right? So as I add more and more items, the value, the information content of f will only increase. Um, this is exactly equal to what I do is that I just so here delta is nothing but the gain, right? So this is nothing but f of vj star given ai union vi star vj minus 1 star, right? So all I'm doing here is that I'm kind of breaking this into basically kind of like a telescopic sum. So if, like many of you have seen proofs of in optimization, continuous optimization, telescopic sums are used all the time, right? So all I'm doing here is writing this as a telescopic sum. So essentially what I'm doing is I'm starting from f of, I'm kind of writing down a telescopic sum for this quantity, which is f of a star within ai minus f of ai, right? And this I can write as a difference between consecutive sets that come in this chain. And I can take any arbitrary chain, by the way, right? So this is how, this is what this particular term would be. Now I apply submodularity, right? So because of submodularity, I can actually take a smaller set of this, which is f of ai, and I can replace this with arbitrary z, right? Because this ai is fixed now. So this is nothing but, so actually this term I'll just rewrite as f of z given ai, right? So I've just used submodularity. All I've done is that I've gone from this equation, replacing this larger subset with this smaller subset. Because I've replaced a larger subset with a smaller subset, I get less than equal to, right? So I only increase it by taking a smaller subset because of submodularity. All right, so I have this, and then what I notice is that at step I, the vi plus 1 is the argmax quantity, right? So I replace this entire thing by this fixed quantity, which is vi plus 1 given ai, and then I have k times this delta, right? So now after rearranging these terms, what we get is this gain, which is f of, which is the greedy gain at iteration ai, is greater than or equal to 1 over k times opt minus f of ai. So I think this is the key step now that we will use for manipulation. The rest of the proof is just simple manipulation on top, right? So what happens, define delta I as opt minus f of ai. Then notice that delta I minus delta I plus 1 is nothing but this gain, right? So this is the gain that we had over here. So this gain, which is delta I minus 1, is greater than or equal to 1 over k times delta I. Right? So this step basically is just rewriting this and introducing delta I. Okay. Then notice that delta I plus 1 is less than or equal to 1 minus 1 over k times delta I. Because what I do is I take delta I plus 1 on this side and delta I on this side, and I just rewrite, just flip the inequalities. Right? So now what I can do is that I can kind of multiply this from I from 0 to k, right? And I get this, because recall that delta 1 would be less than 1 minus 1 over k times delta 0, delta 2 would be less than 1 minus 1 over k times delta 1, and so on and so forth. Right? So I multiply the LHS and the RHS, and I get delta k as less than or equal to 1 minus 1 over k raised to k multiplied by delta 0. Okay. Now recall that delta 0 is nothing but opt minus f of the empty set, right? Without loss of generality, you can assume f of the empty set is 0, but if you don't want to make the assumption, you just notice that delta 0 is actually less than equal to opt, right? Because f of the empty set will at least be greater than equal to 0. We have assumed that the function is greater than equal to 0, right? So hence delta k is less than 1 minus 1 over k raised to k of opt, and this in turn is less than 1 over e of opt, right? Why is this the case? Because 1 minus x is less than equal to e raised to minus x. Okay, so 1 minus 1 over k, so this implies that 1 minus 1 over k is less than e raised to minus k, right? So I raise both to the power k, so 1 minus 1 over k raised to k, oh sorry, this is 1 over k, sorry, excuse me, this is minus 1 over k, right? So this is less than, this raised to k is less than e raised to minus 1. Right? So 1 minus 1 over k raised to k is less than 1 over e multiplied by opt, right, over here. And again, just kind of rearranging this, because delta k is opt minus f of ak, this is less than equal to 1 over e times opt. Rearranging this, we get f of ak greater than equal to 1 minus 1 over e multiplied by opt. Right? So again, it's a very simple proof. Took me probably 5 minutes, maybe three to 4 minutes to go over, but very powerful, right? So most of the proofs kind of on other variants on submodularity, which we'll see, in some way or form actually use the techniques from this. Not exactly, but I mean, kind of the same intuition holds, right? Because you always want to use the notion of submodularity. So if, for example, you don't have monotonicity, then you can, maybe go around it in some way by not having monotonicity, but still kind of getting a result from that, and so on and so forth, right? So you have different proof techniques, which we won't actually cover in this tutorial, like in the interest of time, but just want to give you the main idea of this very kind of fundamental and seminal proof and result from 1978. Okay, so now we will go to one more level of complexity, and instead of having a size constraint, which is size of s less than equal to k, we have a budget constraint, which is basically the sum of e in s, c of e is less than equal to b, right? And the idea of the budget constraint is as follows. So it's not necessary that each of my items that I'm trying to summarize have the same cost, right? So think of an application like document summarization, where I'm summarizing sentences, right? So I'm summarizing a document, but each of my items are sentences, right? So I want to select a subset of sentences that kind of will form a summary of my document. It's called extractive summarization, and in this it actually makes sense to do budget constraints, because uh, your constraint may not be on the size or the number of sentences, but it could be on the word limit. But different sentences could have different number of words, so that's why each sentence has a cost, right, which is the number of words, right? And then you could have a budget constraint like this. So how does this apply for budget constraints, right? Well, what you need to do is you need to run a modified greedy. So this modified greedy actually takes E star equal to argmax of f of Si union E minus f of Si divided by Ce, right? And actually what the theoretical kind of guarantee is for requires that you run both the standard greedy without the cost, without the Ce in the denominator, right? Um, and the modified greedy and pick the better amongst them, right? And that has a half times 1 minus 1 over E. It turns out that you can actually do a partial enumeration. And what I mean by partial enumeration is consider all subsets of size 3. Why is it 3? Well, that really depends on the proof technique. I think I suspect that this can probably be improved, but I don't think anyone has really proved this until now, whether there's a 1 minus 1 over E for the standard greedy algorithm or not. But you do this partial enumeration of order n cube, and then you get this subset. And once you get the best subset, you run greedy on top of that. And that actually has a 1 minus 1 over E. So in fact, you run the cost sensitive greedy, which is the same as this version here. So you can summarize in general, right, for this budget constraints problem, the greedy algorithm as follows. You pick the best cost sensitive item, which is f of v given s divided by c of v, and update it until my budget is satisfied, right? C of s less than p. So as soon as C of s becomes greater than p, I stop. So this is the greedy algorithm, and this has the guarantee we spoke about, right? All right. So now we'll talk about a slightly different problem, which is known as a submodular set cover, right? And in the submodular set cover, what I'm doing is that I'm actually flipping my objective function to from. So if you recall, my optimization problem was a such that size of a is less than k of f of a, right? So in some sense, you can come up with a dual version, which is to minimize size of a such that f of a is greater than q. Okay. So this problem is called a submodular set cover or a submodular cover. So all I've done here is that I'm saying that my function should at least be a certain value. It turns out that this also is actually very natural. Think again of an application like data subset selection, right? Imagine that f measures a loss or an accuracy, right? I want to have my likelihood function or my um, loss function to be as high as possible, right? Or sorry, my loss function to be as low as possible, or my accuracy or likelihood to be as high as possible, right? So, for example, I can say that I want my likelihood somewhere close to the full likelihood, right? So, I want to find a subset A so such that f of A is greater than equal to Q, right? And hopefully, essentially, this could be what is the smallest subset? What is the smallest subset that I can get such that I don't sacrifice anything on accuracy, right? And maybe the answer is for a particular data set, it's 30%, right? So I can kind of remove 70% of the data set without really losing anything on accuracy. But it could be that for a certain data set, it's only I can only remove 10%, right? Um, so I think both versions of the problems are interesting. The budget constraint is interesting if you really have a budget constraint and you want to operate within that budget constraint. It could be resources, for example. You don't have as big a GPU and you want to get your experimental results as fast as possible. You want to do hyperparameter tuning. You really want to operate on a small subset. But you could, but on the other hand, if your goal is really to speed up training without really, sacrificing on accuracy, maybe the submodular cover makes more sense. All right, so I will give just the main idea of matroid constraints. It's not again super relevant right now for some of the applications we'll be talking about, so I won't spend too much time here. But you can actually think about slightly more complicated constraints than just knapsack constraints and budget constraints, and these are matroid constraints. So matroid constraints, one example of a matroid constraint could be where I have configurations of cameras, right? So basically cameras point in a certain direction and I want to select a subset so that I pick only one, like at most one from each of my configurations, right? So say for example, I have my constraints to be P1 is 1A, 1B, 2A, 2B, 3A, 3B, and so on and so forth, right? So I could require that my S of the size of S intersection Pi is less than or equal to 1 for all I. So this is called a partition matroid constraint. But matroids in turn actually generalize many more interesting combinatorial structures. So for example, you could have a uniform matroid, and this is exactly kind of size constraint, right? Partition matroid is basically select at most one element from each group. You could also have a graphic matroid, which basically is like a spanning tree, for example. So spanning tree is an example of a graphic matroid, and so on and so forth, right? So you have many other constraints like this, and they kind of can be fitted in this kind of nice combinatorial structure called matroids. So the properties of a matroid is that if S is independent, T, a subset of S also is independent, right? So independent sets in matroids are basically sets that satisfy this property that you're asking for. For example, if size of S less than or equal to K, then this is an independent set in a matroid. They also satisfy what's known as an exchange property and also have this property that all maximal independent sets should have the same size. So again, I won't dwell too much into this. There are many texts. You can do a Google search for a Wikipedia page on matroids to get just the basic idea of what matroids are. It turns out that a very simple greedy algorithm, extension of a greedy algorithm, works for matroid constraints. You select argmax of f of S union E as long as S union E is feasible, right? And continue this till S union E is feasible, right? So once you hit a maximal independent set, you stop. For monotone submodular functions, the greedy satisfies a half times f of s star over here. So you get a slightly worse factor. So 1 minus 1 over is 0.63. You get a zero point 0.5 now, but it's still constant factor, right? Okay, so now we'll look at non-monotone submodular functions. So you can also relax f to be non-monotone. And here you need to run a variant of a greedy algorithm called a randomized greedy, right? And what the randomized greedy does is that instead of picking the best item, it actually picks the top k items that have the largest gain and randomly picks one amongst the top k, right? So essentially it tries to maximize this sum, and basically maximize this sum is the same as picking the top k and pick y uniform random element from the set mi, right, which is the top k set, and then you add y. So this randomized greedy algorithm actually has the required guarantee, which is 1 over e. Again, slightly worse. 1 over e is roughly around 0.3737. So it's not as good as zero point 0.5 or 1.63, but this is still constant factor again, right? All right, so there is one more slight variation in the formulation where, so we studied first budget constraint, then size constraint, then we studied budget constraints, then we studied submodular set cover, then we studied matroid constraints, right? And then we looked at non-monotone functions. So there is one more variant where you can actually add the constraint as a part of the objective. So something like a Lagrangian, which you're familiar with in continuous optimization, right? So we add this over here, and this becomes now, so even if f is monotone, right? Even if f is monotone, this entire thing is actually non-monotone, because I've subtracted from Cx. It's still submodular because C is additive or modular, but it's not monotone. But now I don't have a size constraint anymore. So this I've converted this into an unconstrained problem, right? And this is now an unconstrained non-monotone submodular maximization problem. It turns out that we can do a bidirectional greedy algorithm here. So what the bidirectional greedy algorithm is that you start with you maintain two sets A and B, and you go down either direction, right? So you start with A equal to empty set B equal to V, and then for I from 1 to n, with a certain probability, you and the probability is based on this delta plus divided by delta plus plus delta minus. Delta plus is the gain of adding this particular item I to the set A, and the delta minus is the gain of removing from set B. And with this probability, you either add or you remove, right? So essentially what this means is that you flip a coin with this particular probability. If the coin, and the coin is P add, right? So the coin says head, you add, coin says subtract. I mean, if the coin is zero, right? Or tails, you actually remove from B, right? So either case, what happens is that A either grows and B shrinks, and it's a randomized algorithm, right? Finally, it will converge at one point after n iterations. The subset it converges to turns out has a half approximation for unconstrained submodular maximization. Okay, there is a slight variant of algorithm for having f being submodular plus dispersion. So dispersion functions, for example, the minimum pairwise distance function is not submodular, but still you can actually combine it with a submodular function and get a constant factor guarantee. So it turns out that you can get a half and a 1/4 guarantee for submodular plus disparity sum and submodular plus disparity min optimization problems. So this was a very nice result by Dasgupta et al. 2013. Okay, so now coming a little bit into the algorithms and the computational aspects, right? So I promised you that the greedy algorithm is very, very scalable, right? That comes with a caveat, right? The greedy algorithm is relatively scalable because just looking at adding one element at a time, but still it has to do the order and search, right? So the complexity of the greedy is order nk times the number of function evaluations, right? Now imagine if k is 5% of n, this would still be order n square. This is not good, right? So there are actually two kind of variants of this which we'll study. The first is what's known as a lazy greedy algorithm, and the lazy greedy algorithm does the following. So it actually implements priority queues and maintains upper bounds on the marginal gains, and essentially based on the priority queues it decides whether to kind of pop an item or not, and it kind of implements this in a lazy manner. So if many of you have kind of studied lazy algorithms in a CS kind of algorithm class, I won't go into the exact algorithm right now, but it turns out that this brings the complexity in practice to be something much faster than the naive greedy, right? um, in still the worst case complexity is still order nkf, right? So there are functions where you need to do a lot of resorting operations, and then it actually becomes somewhere very close to this. So this is still not that great, right? So there was a very recent paper by Mirza Soleiman et al. 2014. I believe it's a AAAI paper, and here the author showed that you can get a provable order n approximation algorithm, which gives an approximation of 1 minus 1 over e minus epsilon, right? So epsilon is this parameter which basically decides how close to 1 minus 1 over you can get. And you trade this off by actually having a log 1 over epsilon here. So you pick a random set t of size n divided by k multiplied by log 1 over epsilon, right? So it's a random set. And you just pick the best item. So again, a greedy algorithm does a search, an order n search, right? This says that you just do a n over k log 1 over epsilon search, right? So it's much, much faster. And because you're doing this k times, the total complexity is actually order n log 1 over epsilon, right? So imagine epsilon is say 10 raised to minus 3, log 1 over epsilon is 3, right? So the complexity is actually 3n. So it's still linear. And with this, you can actually get very close to 1 minus 1 every times approximation. In practice, it actually turns out to perform very well, right? So there are different variations of epsilon, and this is again the performance. It's much, much faster than lazy greedy, right? Sorry. Okay. So there are actually several other optimization problems in submodular optimization, which we didn't actually study in this tutorial. One is unconstrained submodular minimization, which is polynomial time. Then there is constrained submodular minimization. Then there is also difference of submodular minimization, submodular optimization subject to submodular constraints, also called SCSC, SCSK, robust and average cost submodular partitioning. So we didn't talk about submodular partitioning, but again, this is something very natural for many applications in like data partitioning, for example, clustering, distributed training, diversified training, and so on and so forth. Continuous submodularity, online optimization, so on and so forth, right? So I didn't cover a lot of different flavors of optimization algorithms in the interest of time, but we will cover a few more settings. So we will look at two specific settings. One is streaming and one is distributed. So the idea of a streaming algorithm is that data comes in a stream, right? So it's a data stream coming in one by one. And the question is, with this data stream coming in, I want to decide that once I look at an item, I want to decide whether I want to add it or not, right? So I just do one pass over the data set in an online manner, right? The way this algorithm works is that it actually maintains several different subsets. So it's actually got a slightly higher memory cost, right? So it maintains different subsets called sieves, and each of these sieves have thresholds, right? And then once a new item comes, you compare with each of my sieve, right? And then you take the max of the gains given my different subsets, and then you basically decide whether you want to add it or not, right? So it turns out that this sieve streaming algorithm is a single pass half approximation, right? So essentially, the fundamental idea here is that you need to maintain k different sieves or k different possible subsets. And in the end of your stream, you just take the max amongst all of them. Okay. So this algorithm is order n. It's a streaming or an online algorithm, and it's a half approximation. Yeah. It turns out there are a few other improvements over this. Um, there are ways to improve the memory footprint and the computation complexity. There are extensions to other constraints. There have been some work of incorporation of aspects like fairness and also incorporation of concepts like swapping and maintaining running summaries. So basically, um, you might have a scenario where you want to maintain just one summary, but you want to potentially allow for swapping of elements, right? Because you have a very large stream and you want to always maintain a running summary that is representative, right? So imagine you have something that, maybe it's a video and you have a continuous video stream of a surveillance camera and you want to maintain a running summary of this. So this is a recent work which kind of does this. Okay, so now we will look at the second setting, which is distributed greedy, right? So imagine you have massive amounts of data of the order of, say, 1 billion to 100 billion, right? So how do you handle data sets of this size? So what you do here, obviously this data cannot fit into a single machine, right? So you have multiple machines. You randomly split the data in these multiple machines, and on each data set, you run a summarization, right? So you select a size k subset on each of my um, um, machines, right? And I get the k summary. So k is very small, right? Think of k to be, for example, 0.1%. So it's extremely small. So you are just taking those k subsets and you're aggregating them finally over here, and then you get your much smaller subset, right? So again, you actually run greedy. So if there are m machines, this is going to be m times k, and you get greedy, and you run greedy, and you get k. It turns out that this also has an approximation guarantee, but it's not constant factor. So this was one of the first papers to actually study distributed submodel optimization. But then there was a follow-up work which actually showed that you can do something very simple, where you actually have these different k different um, so you have m different machines, you aggregate them, right? But then you actually take the summary and again do one more step of taking the k plus one, or sorry, the m plus one solutions, and again do one more round of greedy, right? Or sorry. So you don't run greedy. What you do is you pick the best amongst the m plus one solutions. That's it. And this, it turns out, has a half times 1 minus 1 over e approximation factor. So this was an interesting paper in 2015, which actually showed this result for distributed greedy. Okay, so finally, we have weakly or pseudo submodular functions or pseudo submodular optimization. And a number of natural functions are actually pseudo submodular. And there are actually a few different approaches of solving this, or looking at pseudo submodularity. One is where you define this for monotone functions, right? So this is the definition for monotone functions, and this is the definition for non-monotone functions, right? Essentially, what pseudo submodularity says is that if this were submodular, then this particular value, then gamma would be 1 over here, right? But pseudo submodularity allows for gamma not to be 1, say gamma being less than 1, and still you can actually kind of get a submodularity result here, right? So you have gamma weakly submodular, and then you have submodular, modular, and gamma pseudo submodular. So if gamma is greater than 1, f is submodular, right? For non-submodular functions, gamma is between 0 and 1. And if f is monotone, then pseudo and weakly submodular are the same. But for non-monotone functions, the weakly submodular actually makes sense. So this is, again, there have been quite a few number of papers that have studied this notion of weakly submodular and gamma weakly submodular functions. But the main point is that you can get a theoretical guarantee, right? So you can show a 1 minus e raised to minus gamma for a gamma weakly submodular function. You can show a gamma multiplied by e raised to minus 1 over gamma for a gamma weakly submodular in a non-monotone case, right? In the monotone case, is 1 minus e raised to minus gamma. Okay, so now to end, right? I'll actually end with this, and then I'll just go over a few different toolkits for submodel optimization. So this will be the last two things which we'll cover. So first, we'll talk about memoization, right? So memoization was actually a recent paper which actually showed that you can do this very simple trick of pre-computation, and pre-computation actually kind of works at a function level, right? So for each specific function, you can cache the kind of intermediate variables and maintain this pre-computed statistics for each subset X. But as the greedy algorithm proceeds, you can use the statistics to actually compute the gain much faster. So given the pre-computed statistics, the evaluation of the gain is much more efficient. Right? So it turns out that this gives significant speed ups compared to just simply using the value oracle model. And for a number of functions, you can actually come up with these pre-computed statistics, right? And this actually almost always reduces the complexity by a factor of n, or a factor of size of x, or something like that, right? So this is, in some sense, a very kind of practical kind of trick that is used, and most of the libraries today that kind of implements about optimization do this. So we will actually review. So this is actually an example of the role of pre-computed statistics, right? So this is a lazy greedy algorithm, and these are two other algorithms which we didn't cover in this tutorial. One is a minimum norm point algorithm, and the other is SCSC, submodular cover, submodular constraint. Um, so we see first of all that the with memoization that this scales very well, even up to like 10 million, right, on a single CPU. Of course, you can do distributed versions where again you do memoization and the complexity remains the same. Once you go to a billion, or maybe order of a billion size data sets. But the with or without memoization, we see that there is this drastic reduction, right, with memoization. So basically, for example, with lazy greedy, with facility location, the time goes from 48 seconds to 0.31 seconds. I think this is for the 4,000 size data sets, right? Of course, once you go to much larger 100,000, it won't even run without memoization. So you have to really use memoization. All right. So with this, let me quickly pull up a few different toolkits. So the first one is submodlib, which basically is based out of C++, but has an extension in Python, right? So basically both of these are Python toolkits. There's a slightly older toolkit in MATLAB called SFO. I won't actually be covering that, but you can feel free to check that out as well. I'll actually pull that up also in the interest of completeness. Yeah, sorry. Yeah, just give me a minute. Sorry, I'm just pulling. I'm just pulling this up. So yeah. So what I'm going to do is I'm just going to make this a little bit smaller and bring this page up. Sorry. Okay, so the first one is called Submodular, and this is actually created by one of my and Ganesh's students, Vishal Kaushal. Um, and This one is, as I was saying, is built on C++, but it has a front end in Python, and the use case of this is very simple, right? So you just say from submodular functions or facility location import facility location function, and then you can kind of define the facility location here as facility location, define the n as the ground set size, the data set that you want to define, the the mode of defining the kernel and the metric for the kernel, right? And this also internally actually computes the kernel for you. And then you do greedy list equal to objective fl dot maximize, and then this gives here you also give the algorithm. So this is like naive greedy, but you could do lazy greedy, stochastic greedy. So there are several functions implemented here, and several mutual information functions, and also several optimizers. So a lot of this is work in progress. This is still being developed actively. Hopefully, in a month or so, we will actually have the next release, which will have most of this implemented. But there is a slightly more stable toolkit which was built in Python again. But unlike Submodlib, this is actually done completely in Python. So it might be a little bit slower because it's Python based, but I think this also equally offers the same amount of utility, right? So this also implements a number of submodel optimization functions, a number of optimizers, and there is also this is also very similar, right? So you get import facility location, and then you do facility locations selection, and basically have the number of data points here, metric, optimizer, and so on and so forth. So again, this is something I would definitely encourage you to get a hands-on practice on if you're interested in some modularity and would like to use this. Third toolkit is a MATLAB toolbox on submodule optimization. This one, unfortunately, is in MATLAB, so it's not as useful, but it is still it's still there. It's a little bit slower, but it's also based on proprietary software that is MATLAB. But these are the three options. I would definitely encourage you to try whichever one you are more familiar with, and give it a shot. Okay. All right. So with this, actually, we'll end. These are all the references for the toolkit. Sorry. So let me just, yeah. So these are the references, and I'll be putting the slides up on the tutorial webpage as well. Thank you so much for your patience and for attending the first part. The second part of the tutorial will be covered by Ganesh Ramakrishnan. All right. Thank you so much. Have a nice day.